Welcome to today's paper reading. Today's paper is titled SparseSSP, 3D Subcellular Structure Prediction from Sparse-View Transmitted Light Images. This paper was published on ECCV by Jintu Zheng and colleagues from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. The abstract highlights the limitations of traditional fluorescent staining, which is harmful to live cells, slow, and expensive. To address these issues, the authors introduced SparseSSP, a framework that predicts subcellular structures from transmitted light images without labels. This approach is faster and more cost-effective. SparseSSP introduces two major improvements: a one-to-many voxel mapping paradigm and a hybrid dimensions topology. These innovations allow the framework to reduce the need for Z-axis imaging and lower computational costs, making it more efficient than previous 3D topology-based methods. Fluorescence microscopy is crucial for visualizing subcellular structures in 3D, but it requires expensive equipment and time-consuming preparations. SSP technology predicts 3D immunofluorescence from transmitted light images, reducing costs and minimizing phototoxicity. However, existing methods require dense imaging processes, which are not ideal for capturing rapid biological dynamics. Sparse-View SSP is therefore desired to address these challenges, making it significant for low-cost devices and live cell studies. Figure 1 illustrates the differences in subcellular structure prediction (SSP) implementations. Panel A shows MultiNet, which employs a set of independent 3D models for SSP. Panel B depicts task embedding, an improved strategy that relies on one-hot encoding for all tasks but still necessitates a dense imaging procedure, leading to prolonged imaging time and high computational costs. Panel C introduces SparseSSP, which implements an efficient hybrid dimensions topology, requiring fewer transmitted light (TL) imaging slices to achieve excellent performance. This approach significantly reduces imaging frequencies and computational overhead, making it more suitable for rapid biological dynamics visualization on low-cost devices. The partially labeling issue in subcellular structure prediction (SSP) arises due to the high cost of labor and limitations in simultaneous multiple staining. This issue is similar to many medically dense prediction tasks. Fortunately, there are mature solutions available for multitask learning. MultiNet approaches use independent networks to learn tasks, but they are inefficient and inflexible in tuning network parameters. Sparse-View techniques have emerged as a significant area of research, offering benefits such as reduced radiation dose and lower phototoxicity, allowing for better observation of rapid biological dynamics. SparseSSP aims to predict the target voxel grid S from the imaging voxel grid I under the condition DSD. This involves reducing imaging frequencies by using a sparsity ratio R. The dataset P contains N samples with fluorescent labels YN and TL inputs XN. The one-to-many mapping in the Z-axis is addressed through prefix and postfix interpolation strategies, which involve creating a pseudo-voxel grid S and learning a mapping to S. Figure 2 illustrates the various strategies and topologies employed in SparseSSP. In Part A, two strategies for one-to-many mapping in the Z-axis are shown: prefix and postfix interpolation. These strategies aim to handle the sparsity in the Z-axis by either interpolating before the network, or learning a mapping followed by interpolation. Part B presents four combinations of different dimension encoders and decoders, including 2D, 3D, 2 to 3D, and 3 to 2D topologies. These hybrid approaches aim to balance computational efficiency and prediction accuracy. Finally, Part C demonstrates diverse methods for implementing dimension transformation, specifically depth-to-channel and channel-to-depth transformations. These methods enable the efficient handling of 3D information using 2D network layers, facilitating the modeling of Sparse-View voxel grids. Figure 3 provides an overview of the SparseSSP framework, specifically detailing its 3 to 2D topology with prefix interpolation. This figure exemplifies the framework's design following the DuDiNet style, which incorporates a task controller and dynamic head. Notably, the framework's task embedding approach is modular and can be easily adapted to other technologies, showcasing its flexibility and potential for integration with various state-of-the-art methods. The experiments are conducted using the Allen cell collection, which includes 12 distinct subcellular structures. The data distribution involves selecting 25% of samples for evaluation and 10% of the remaining data for testing. Pre-processing steps include z-scored normalization for voxels and data augmentation, following the rep mode's data splitting method. The fluorescence labels and TL input images are resized to specific voxel dimensions. The evaluation metrics are based on the rep mode standard, utilizing 3 key metrics to assess performance. The sparsity ratios of 2, 4, and 8 are compared, with a ratio of 8 indicating an 87.5% reduction in imaging frequencies. The SparseSSP framework introduces a novel approach to subcellular structure prediction, SSP, by employing a hybrid dimensions topology. This method enables efficient SSP using sparse transmitted light, TL, images, significantly reducing the need for extensive microscopy imaging and computational resources. By leveraging a one-to-many voxel mapping paradigm, SparseSSP implicitly refines sparse z-axis information and converts it into channel features, allowing advanced 2D modules to handle 3D SSP challenges effectively. Extensive experiments with state-of-the-art multitask methods across various sparse ratios have validated the effectiveness and advantages of this approach. This work represents a pioneering effort in utilizing Sparse-View TL images for SSP, advancing the field of rapid biological dynamics visualization on low-cost devices and samples. Figure 4 illustrates the trend of our two values as the sparsity ratio increases from 2 to 8. The hybrid dimensions topology 3 to 2D, represented by blue lines, demonstrates a slower decay and higher global scores compared to the pure 3D topology, indicated by orange lines. This suggests that the 3 to 2D topology maintains better prediction quality as the sparsity ratio increases, highlighting its effectiveness in Sparse-View subcellular structure prediction. Figure 5 presents a visualization of subcellular structure prediction through a stereoscopic volume display from a top-down z-axis view. The figure compares the results of 4 structures using both dense view and sparse view transmitted light, TL, images at various sparsity ratios. The second column of the figure displays the results obtained using rep mode, which is considered the best approach for dense view subcellular structure prediction, SSP. Columns 3 to 6 show the results from TNET, which employs the best 3 to 2D topology specifically optimized for sparse view images. This comparison highlights the effectiveness of different methods in predicting subcellular structures under varying imaging conditions. Figure 6 presents a comparison between pure 3D and our hybrid topology solution on TGNet. The yellow bounding boxes highlight regions where significant prediction errors occur. This figure is crucial for understanding the performance differences and resource consumption between these two approaches, providing insights into the effectiveness of our hybrid topology solution. Table 1 illustrates the impact of different interpolation strategies on subcellular structure prediction. The data shows that prefix strategies significantly outperform both no interpolation and postfix strategies. Notably, no interpolation is constrained to 2D decoding methods. The table highlights that grayback areas represent the optimal settings for each strategy, indicating superior performance in terms of MSE, MAE, and our two metrics. The sparsity ratio, R, of the input voxel grid is also a critical factor, with different ratios 2, 4, 8 affecting the results. This table provides a clear comparison of how various interpolation techniques influence the accuracy and reliability of subcellular structure predictions. Table 2 examines the impact of projection space and dimension transformation, comparing 3D and 2D implementations based on DuDNet 28. The study reveals that 3D projection significantly outperforms 2D projection, as it better maintains spatial context for 3 to 2D topologies. Additionally, for 2 to 3D transformations, 3D projection allows for the pre-reconstruction of a 3D space, which is then refined during layer-by-layer upsampling. This approach demonstrates superior performance in preserving spatial integrity and refining complex structures. Table 3 presents a comparison of various topologies for Sparse-View subcellular structure prediction, SSP. It evaluates the performance of mainstream multitask approaches implemented in different topologies. For hybrid dimensions topologies, such as 3 to 2D and 2 to 3D, the 3D space projection is employed in the dimension transformation. All experiments utilize prefix interpolation to incorporate prior spatial knowledge into the model learning process. The red bold row indicates the strategy with the lowest mean squared error, MSE, and mean absolute error, MAE, as well as the highest R-squared, R2, value. The rows highlighted in gray represent the winning strategies within their respective groups. Table 4 investigates the effect of increasing training epochs on the 2DNet model to determine if the 2D encoder requires more time to converge. The table presents data for different training epochs, 7,000, 14,000, 3,000, across two topologies, 2 to 3D and 2D. Key metrics evaluated include mean squared error, MSE, mean absolute error, MAE, and R-squared, R2. The results indicate that longer training epochs slightly improve performance, suggesting potential for further optimization. Table 5 presents an ablation study on 2D backbones, specifically focusing on the TSNs, which generally show inferior performance compared to other implementations. To enhance performance, the 2D backbone was replaced. The results indicate that transformer-based backbones significantly improve performance, suggesting the potential to integrate more advanced 2D network technologies into the framework, such as the latest transformer designs. Table 6 presents a detailed comparison of resource consumption across different network topologies, specifically focusing on TSNs, 2DNet, and rep mode. The data clearly indicates that hybrid dimension topologies, which combine elements of both 2D and 3D approaches, significantly reduce resource usage compared to purely 3D topologies. This reduction is particularly evident in the number of multiply-accumulate (MAC) operations, a critical metric in computational efficiency. The table also highlights the number of iterations in training, which corresponds to the number of loss backward operations, providing insight into the training process efficiency. This comparison underscores the potential of hybrid approaches to optimize resource usage and network design, potentially paving the way for more efficient and scalable solutions in the field. Table 7 presents a detailed comparison of various structures across different sparsity ratios. The FNet serves as the reliable baseline for evaluating the performance of the proposed methods. Among these, the TNet 3 to 2D configuration is identified as the optimal setting within the SparseSSP framework. This configuration demonstrates robust performance across different subcellular structures, making it suitable for practical biological research applications. Notably, even with an 87.5% reduction in imaging times, SparseSSP exhibits only a minor decline in performance, highlighting its efficiency and effectiveness. Thank you for watching.